Imagine a line, a simple unbroken line, stretching into infinity. This line, in its purest form, represents the first dimension, a realm of length but without depth, a universe infinitely long but impossibly thin. Now, let's broaden our perspective by introducing a second line intersecting the first, and suddenly, we're in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a foreign concept. As we take one step higher, we find ourselves in the familiar embrace of the third dimension. This is where depth comes into play, adding volume and substance to our world. Buildings rise, valleys deepen, and the universe takes on texture and shape. But what if we add another layer? Time is the elusive fourth dimension that permeates our three-dimensional space. It's invisible but omnipresent. It dictates the rhythm of our lives, a continuous thread connecting each previous moment with the current one, and the current one with the next. In this realm, our understanding of reality becomes more complex and broader. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our sensory perception. However, nature hints at even more complex dimensions. In the field of physics, theories suggest the existence of dimensions beyond our perception, necessary for the fundamental forces that govern the universe. These higher dimensions, though beyond our sensory perception, are crucial to understanding the structure of the cosmos. Join us as we try to unravel their mysteries together, one dimension at a time. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of modern physics. Philosophers once pondered the nature of existence, laying the foundations for our understanding of space. In their discussions, they questioned the very essence of reality, imagining realms beyond the tangible. As the centuries passed, these philosophical speculations paved the way for more structured inquiries into the nature of the universe. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities but intertwined dimensions that form the fabric of spacetime. Albert Einstein, in turn, built upon the foundation laid by Minkowski, presenting the revolutionary theory of general relativity. This theory restructured our understanding of gravity, space, and time into a single continuum, forever changing the course of physics. Thus, from the philosophical quest of ancient thinkers to the scientific revolutions sparked by Minkowski and Einstein, the journey through the evolution of spatial thinking reveals a relentless quest to comprehend the true nature of our universe. Over time, we've come to realize that to truly comprehend the fabric of our reality, we must go beyond the three tangible dimensions into the realm of the fourth dimension, time. The concept of time as a dimension is both profound and persuasive to our existence and the universe as a whole. Unlike the three spatial dimensions, time has a direction. It moves inexorably forward from the past, through the present, and into the future. This unidirectional flow of time distinguishes it from space, giving the universe a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, consider a simple everyday scenario, organizing a meeting. When we suggest that someone meets at a certain place, we unconsciously navigate the three basic spatial dimensions to determine where. It makes sense that if we arrived at different places, no meeting would take place. However, the when, the dimension without which the meeting will not happen, is no less important. If you and your friend come to the same place but at different times, you won't be able to see each other. This intertwining of space and time is manifested in the concept of the world line, the path that an object or person takes through spacetime, thus representing its history and future. The idea of world lines provides a vivid illustration of how events are linked together in the fabric of spacetime. For two people to meet, their world lines must intersect at a precise point in both space and time. This intersection is not just a coordinate but a spacetime coordinate, the only point in the vast continuum of the universe where both where and when coincide. This principle applies not only to simple encounters but also to the fundamental workings of the cosmos. Celestial bodies, from planets to stars, trace their own world lines through spacetime, their paths determined by the interplay of spatial positions and temporal moments. For example, the Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space to the dynamic unfolding of events. Time allows us to understand the universe not as a set of individual moments but as a continuous narrative where cause and effect bind our reality into a coherent whole. The inclusion of time as a dimension has catalyzed major advances in physics, particularly through Einstein's theories of relativity, which we've already mentioned. These theories not only deepened our understanding of the cosmos but also paved the way for new research in quantum mechanics and cosmology. Einstein's revelation that time is relative, it slows down or stretches depending on the velocity of an object, challenged the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different reference frames. This phenomenon is confirmed by experiments, such as those involving atomic clocks on fast-moving airplanes. In quantum mechanics, time as a dimension underlies the evolution of a particle state, governed by the Schrödinger equation. This basis is important for understanding phenomena such as entanglement and superposition, where the time dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm where our everyday experience and the laws of physics as we know them are fundamentally challenged and expanded. In search of a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity, physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes even more intricate and mysterious. The fifth dimension and beyond are not just speculative constructs but important components in the quest for a deeper understanding of the universe. In theories such as string theory, these higher dimensions offer solutions to physics' most challenging mysteries, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions lies in the fact that our perception is inherently three-dimensional. Therefore, analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called the flatlander, living in a flat, two-dimensional world. This being can move forward and backward, left and right, but has no concept of moving up and down because these dimensions do not exist in its two-dimensional experience. Imagine a three-dimensional sphere passing through this two-dimensional world. To a flatlander, the sphere would first appear as a dot when the sphere is just touching the two-dimensional plane, gradually increasing into a circle as more of the sphere passes through the plane, and then decreasing again to a point as the sphere leaves the plane before disappearing altogether. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears without realizing that a three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, posits that particles are not the individual points we see them to be, but tiny vibrating strings whose modes of vibration determine the properties of the particles. This theory requires the existence of more than the four known dimensions. In fact, it suggests that there may be as many as 10 or 11. These additional dimensions are compacted or convoluted so that they are imperceptible on our scale, like the sphere in the flatlander example. In the fifth dimension, we encounter a space containing all possible universes that start from the same initial conditions as our own universe. Imagine a tree, each branch representing a different decision or outcome, leading to a different reality, all coming from the same trunk. Just as a person standing at the base of the tree can choose which branch to climb, a being with access to the fifth dimension can explore these alternate realities, each a variation of our own universe but with slightly different outcomes. The ascent to the sixth dimension opens up a plane containing all possible universes with the same initial conditions as ours but with any possible set of laws of physics. If we think of each universe as a sheet of paper, the sixth dimension would be like a stack of sheets, each representing a different universe. A being capable of traveling through the sixth dimension could hop between these universes, learning the different outcomes and laws governing each reality. The seventh dimension extends this concept to include universes that start from different initial conditions. To use a library analogy, each book represents a different universe. The seventh dimension encompasses the entire library, offering not just different stories, universes with the same initial conditions as ours but with different outcomes, but completely different genres, universes with different initial conditions. A seven-dimensional being could move through this library, experiencing an infinite number of universes, each with its own unique initial conditions and physical laws. In the eighth dimension, we find a web of all possible universes, each with its own initial conditions and laws of physics, as well as all possible variants of their development in time. Imagine a huge web where each thread represents the timeline of a separate universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The eighth dimension encompasses this entire web, allowing you to travel between any nodes, exploring the connections between different universes and their history. As we approach the ninth dimension, we encounter all possible laws of physics and initial conditions that have existed or will ever exist. This dimension can be compared to the art of origami, where a single piece of paper can be folded into numerous shapes. Each fold represents a change in the initial conditions or laws of the universe, and the ninth dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being living in the ninth dimension would not just have absolute freedom to cross the boundaries between all possible realms of reality, it would experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It's the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline, and all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is challenging because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within that universe. Moving from the trunk to the leaves, we move from the initial conditions of the universe, lower dimensions, through the various choices and events, higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point where all these possibilities come together, the singularity of infinite potential outcomes. It suggests a cosmos in which all possible outcomes not only can happen but happen in some timeline or universe. In the 10th dimension, the concept itself invites us to reflect on the vastness of possibilities that lie beyond our observable universe. It raises questions about fate, choice, and the underlying structure of the cosmos, prompting a broader exploration of potential realities that may exist beyond our immediate perception. The study of higher dimensions beyond our familiar three-dimensional space and fourth-dimensional time has profound implications for both physics and cosmology. This field of study not only challenges our fundamental understanding of the universe but may also hold the key to uniting the disparate forces of nature, potentially solving some of cosmology's most enigmatic puzzles. Recognizing the existence of higher dimensions plays a crucial role in the search for a theory of everything, a single framework that seamlessly unifies general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the inner world of subatomic particles. Higher dimensions may also offer new insights into cosmological mysteries such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter may be the gravitational effects of matter in parallel branches, a concept from M-theory, which proposes multiple parallel membranes or branes as fundamental components of the universe, each potentially containing another universe in higher dimensions. Looking to the future, mastering the intricacies of higher dimensions could pave the way to harnessing forms and mechanisms of energy that we cannot yet imagine, potentially leading to the creation of clean, virtually inexhaustible sources of energy. Similarly, space travel could be revolutionized by a better understanding of the fabric of spacetime, perhaps eventually enabling warp drives or other forms of faster-than-light travel, concepts that are currently in the realm of science fiction but could theoretically be plausible within higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle accelerators such as the Large Hadron Collider at CERN, looking for evidence of additional dimensions and the particles that may inhabit them. This experimental work is complemented by theoretical studies that delve into the abstract realms of high-dimensional spaces, conducted by physicists and mathematicians. As we complete our journey through the dimensions, from the simplicity of a line extending into infinity to the unfathomable complexity of the 10th dimension, we face the inherent challenge of visualizing spaces beyond our three-dimensional experience. Through mathematics, we can describe properties and relationships within higher dimensions, and physics offers theories such as string theory and M-theory that hint at the existence of these additional dimensions. Animation, such as tesseracts, allows us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe, just as the transition from a flat Earth to a spherical Earth many centuries ago broadened humanity's horizons. This expanded perception has the potential to influence not only science but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place in it. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan-3, India's daring journey into uncharted territory. Launched on a journey of more than 238,000 miles, Chandrayaan-3 embarked on a mission not just of distance but of discovery. Its purpose was to unravel the mysteries of the moon's south pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that it is like navigating through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake the silent world? And the most exciting question, does water, the elixir of life, exist here in the form of ice? When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear yet challenging, to achieve a soft landing near the moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, ISRO, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the void of space, overcoming the challenges of lunar orbit insertion and descent. The south pole of the moon is a landscape unlike any other. The terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, and shadows hide frigid temperatures that can drop to -382 degrees Fahrenheit. As the landing module made its final approach, the hearts of the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking a historic moment not only for India but for lunar exploration in general. In the silence of the Moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. After this historic landing, a new chapter in lunar exploration began. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the Moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, were designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the Moon's ionosphere. This layer, formed by solar energy ionizing atoms in the upper atmosphere, plays a crucial role in lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, Chandra's Surface Thermophysical Experiment, CHASE. The temperature probe, immersed in the lunar regolith, was tasked with mapping the thermal profile of the lunar soil. The results from Chandrayaan-3 revealed a sharp contrast in temperatures on the surface. During a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit, while just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit. This demonstrated the lunar soil's potential as a thermal insulator, offering new opportunities for future lunar habitats by suggesting that the lunar regolith could protect astronauts from the Moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the Moon could serve as a gateway to further space exploration. The mission's results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the Moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the Moon. The Instrument for Lunar Seismic Activity, ILSA, a seismic instrument, was designed to detect the slightest tremors on the Moon, and it did. Chandrayaan-3 detected what appeared to be a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences quakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. Chandrayaan-3 data suggests several possible causes for these quakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the Moon's crust. Another is Earth's gravitational pull, causing tidal forces that strain the lunar crust. And finally, extreme temperature fluctuations on the Moon's surface can cause expansion and contraction, leading to quakes. These quakes are not just surface phenomena, they are windows into the Moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of the satellite's interior, resembling a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the Moon. The detection of a lunar quake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor but also opened up new insights into the geological processes that shape the Moon. To unravel the geological mysteries of the Moon, Chandrayaan-3 carried out further exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The laser-induced breakdown spectroscope, LIBS, on the rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the Moon in the past. Its presence could provide insight into the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that has intrigued scientists for decades. Water ice on the Moon is not just a scientific curiosity, it's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the Moon's surface. However, the lack of direct evidence is not a conclusion but a clue, leading to new hypotheses. One theory is cold trapping, where water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released due to the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its presence more heterogeneous and elusive than previously thought? During its exploration of the Moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIDS, laser-induced breakdown spectroscope, instrument made the first-ever in-situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements revealed the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's south pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX. This joint venture between the Indian Space Research Organization, ISRO, and the Japan Aerospace Exploration Agency, JAXA, is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and the rover, while ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved using a feature-matching algorithm and navigation equipment derived from JAXA's Smart Lander for Investigating Moon (SLIM) mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet (1.5 meters). Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage, scheduled for launch by 2028. Chandrayaan-4 will consist of 4 modules, a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of their predecessors, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant but also that of a pioneer. Such achievements inspire us to look beyond and explore the boundless mysteries of the cosmos. The solar system has served as a reliable bulwark for life, but one day humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellites in the solar system. The size of our Earth, these hidden giants have an amazing feature: life could be found in their interior many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system and the search for places where life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets in our visible universe in the following years. In 2009, the Kepler Space Telescope was launched to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets with sizes and conditions similar to Earth's. As of now, we know of more than 5,500 planets outside the solar system, and the recently launched James Webb Telescope is likely to show us even more distant planets. Further, in 2013, scientists were able to determine a planet's color for the first time, and a year later, they recorded its magnetic field and volcanic activity. Finally, in 2018, astronomers made a potentially breakthrough discovery, recording a possible exomoon near the planet Kepler 1625b. While this may not seem like an incredible discovery at first glance, exomoons open a new chapter in modern astronomy. They are not only novel, unexplored space objects but also potential elements for supporting life on exoplanets and their satellites. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the universe's history. But how did scientists manage to confirm so many planets in such a short time when it's impossible to take a photo of each one? Only 69 planets were found with images. The most common method is the transit method, which you may already know. When an exoplanet passes by its central star, the star becomes slightly dimmer, revealing the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet and may sometimes be just a glitch, it is currently the most effective. Exoplanet exploration plays a crucial role in all of astronomy and the future of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are not of much interest to current research. The main problem with searching for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult, and to some extent, even impossible, task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet, but a satellite orbiting it almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation. Due to a completely insignificant change in the brightness of the star, even the first exomoon found by Kepler, and those discovered later near the planets Kepler 1708b and Kepler 1513b, are still not perceived as full-fledged proof of their existence. Therefore, there is a possibility that it could be just a technical error during observation. This is not far from the truth, as further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. The huge size of a possible moon may become one of the most important elements in the further search for other moons. Currently, more than 20 exomoon candidates are known, and all of them are gigantic, at least for Kepler 1625b. The star around which it orbits is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of producing a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it's possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets, like Earth, are still of much higher importance in scientific circles. However, we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe, but this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, 5,268 kilometers, but recorded exomoons can reach the size of the Earth or even Neptune. Therefore, since such moons are difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many features similar to planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future, which is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small sizes, could hypothetically be havens for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere but also have more access to building chemicals both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. The main argument for exomoons as one of the most intriguing places for life to exist is their access to multiple heat sources. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the moon's interior in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time and bringing various crucial chemical elements to the surface. So, exomoons are not as simple as they may seem. Perhaps the difficulty in finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. The analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex, intelligent life has developed. The Earth may hypothetically be almost the only planet on which life could have formed, at least in the visible universe, and any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter for the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is still alive. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for micro signs of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. If interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Pluto mission, which will continuously observe several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this anticipated discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen our knowledge about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of biosignatures or even technosignatures created by civilizations on various moons can provide a clear picture of the signs of intelligent life development. This can help build more prioritized paths for future missions to the most likely planets or moons where alien life might exist. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and perceived insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome and mysterious cosmos one day become less confusing to us. However, in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcomes may be. Saturn has captivated the human imagination from ancient civilizations to modern astronomers. The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How they knew remains a mystery. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape, raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies, they are potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes. However, it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. Here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a pararo or belt around it. How they knew this remains a matter of debate and speculation, but as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that has puzzled scientists for decades. This six-sided wonder is not just a superficial feature but a deep and enduring mystery that challenges our understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft, but it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So, what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse into this extraterrestrial phenomenon. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of gas giants from those of Earth-like planets. The longevity of the hexagon is another mystery. It has been observed for at least 4 decades and possibly much longer. This study feature suggests that everything feeding the hexagon is not a temporary phenomenon but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They are dynamic, ever-changing systems that intrigue astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice, with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static, they are in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps such as the Cassini division, a gap 3,000 miles wide between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they are the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They are slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The demise of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ring giant of our solar system, is not just a celestial wonder, it's also a cosmic playground that contains some of the most intriguing satellites, two of which, Titan and Enceladus, have fascinated scientists and sparked debates about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics and perhaps even its potential for the existence of life? With an atmosphere rich in organic compounds such as nitrogen, methane, and the possibility of an underground ocean, Titan is a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that is very different from Titan. It's an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it on Earth. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but they are quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity as we ponder the possibilities of life on Saturn's satellites. It's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these sites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan, scheduled for launch in the 2030s. This rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we've mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, the material in Saturn's rings, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle, it's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few hundred million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon, or perhaps the capture of a passing comet? Cassini's space dust analyzer has added another layer of complexity. Over 13 years, it collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory or cleanroom, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark, and their disappearance would not only change Saturn's appearance but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. Our universe hides a mystery that has long captivated the human mind, a question that bridges the gap between the known and the unknown, the simple and the complex. Here on Earth, life thrives in a continuous movement of order and chaos. Every form of life is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained not only through the lens of biology but also through a mathematical framework? This is the territory of assembly theory, a groundbreaking concept that transcends traditional science. It's a journey into a world where math and biology converge to reveal the hidden architecture of life. Imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and are waiting to be decoded. In this universe, the line between living and non-living is blurred, giving birth to new possibilities and new understanding. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. Perhaps we can even get closer to answering the ultimate question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been the language of the universe, a tool for deciphering the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life? At its core, Assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Think of life as a jigsaw puzzle where each piece represents a molecular building block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap of complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index. The assembly index, the cornerstone of this theory, measures the number of steps required to build a biological structure. It's a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit into this? The standard model theory of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from the complexities of biology. However, assembly theory bridges this gap. In the field of assembly theory, the standard model lays the foundation for understanding forces and interactions. It's a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamical systems phase space. This is a mathematical concept used to describe all possible states of a system. In the context of assembly theory, phase space allows us to map the path of the assembly of life. From a single point representing the simplest form of life, a space expands, branching out into almost infinite possibilities, each pathway representing a different route that life can take. In this limitless mathematical landscape, the paths of evolution and its complexities unfold. This mathematical framework gives us a new perspective on the complexity of life. It's not just about the particles and forces described by the standard model, but how these elements combine and interact over time to create the diverse pattern of life we see around us. This is where the chaos of random molecular interactions gives way to the order of living structures. So, let's ask ourselves this question: are the complexities of life simply the product of chance, or is there a deeper cause? Let us consider two sharply contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to be at odds with the complexity we observe in life. How do these opposing forces coexist in the natural world? It's here that assembly theory offers a revolutionary perspective. Central to assembly theory is the assembly index, a revolutionary tool designed to measure the complexity of life. Think of it as a cosmic ruler, measuring the steps required to assemble a biological structure from its simplest components. Imagine a single molecule as the starting point on this scale. As you move up the scale, each step represents a more complex assembly, from molecules to cells and beyond. The higher the index, the greater the complexity and the less likely it is that the structure could have arisen by chance. Now let's delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems naturally tend toward disorder. However, life defies this tendency, evolving from simple origins into a variety of forms combined into the complex, ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the lens of the assembly index, we see that the complexity of life is not a challenge to entropy, but a journey through it. Consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began to assemble into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. Rethinking evolution through assembly theory, we see it not as a mere biological process but as a mathematical inevitability. Let us now turn to a seemingly trivial but profound question: are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool in this cosmic quest. Assembly theory offers a unique approach to detecting alien life. It's not about scanning the sky for radio signals or analyzing light spectra for the presence of oxygen. Instead, it's about understanding the complexity of molecules and structures that may indicate life. Imagine scanning the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples in search of patterns that indicate the presence of life. The higher the assembly index, the more likely it is that these molecules result from life rather than random processes. However, the road to discovering alien life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know, life on Earth. What if alien life doesn't meet our biochemical standards? Another problem is the vastness of space. The universe is immense, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can only analyze a tiny fraction of the cosmos. Moreover, assembly theory, while powerful, is still in its infancy. It's a new approach, and its application to the search for extraterrestrial life is uncharted territory. There are questions about its applicability and accuracy in different environments, especially those very different from terrestrial conditions. Despite these problems, the potential of assembly theory in the search for alien life is enormous. It could redefine our understanding of life in the universe, opening new doors in astrobiology. Assembly theory offers a new way of looking at life, not just as a biological phenomenon but as an emergent property of cosmic complexity. Imagine the early days of our planet, a world in motion, a crucible for the chemistry of life. Here, in this chaotic environment, simple molecules began the journey of assembly, a process governed by the laws of physics and chemistry but leading to something much deeper, life. According to assembly theory, life emerges when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory, a crucial step in the evolution of life, comes into play. Chemical memory is the ability of certain molecular structures to retain and reproduce their configuration. In other words, it serves as the blueprint for life. In the world of assembly theory, this is where reproducibility becomes key. The ability to reproduce these patterns, to pass them on from generation to generation, drives the evolution of life. From the simplest RNA molecules in the primordial soup to the vast diversity of life we see today, each step in this evolutionary journey has been a step up the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just one of increasing complexity, it's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the depths of the ocean to the fringes of space. In the realm of scientific discovery, every new theory is scrutinized and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, now stands at a crossroads, being questioned by critical voices such as Dr. Hector Zinal. The critique presented by Zinal raises fundamental questions about the future evolution of assembly theory. Covering an impressive 18,000 words, the article requires time and thought, taking approximately 1 to 2 hours of dedicated reading. This is not a cursory look at the topic, but a deep dive into the heart of the scientific debate. For those interested, we leave a link in the description to both articles, the study and the counterarguments to it. Looking to the future, the role of assembly theory in scientific research remains uncertain. Will it be able to adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear: the debates surrounding assembly theory have initiated a conversation about the nature of scientific discovery. They emphasize the need for transparency, rigor, and humility in pursuing knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, such theories will come and go, but the quest for understanding, the quest to unlock the mysteries of our existence, will always remain at the center of scientific research. Imagine a single point, just a speck of light hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now multiply that image by 100 billion, and even then, you've barely touched the surface. Beyond our Earth, beyond our Sun, and even beyond our galaxy lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans, but how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinew and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now imagine a web woven not by spiders, but by the very fabric of space and time itself, a web that links galaxies, star clusters, and dark matter into a complex network. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network its structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now observe. One of the most impressive examples of a galactic filament is the Great Wall of Hercules, Corona Borealis. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise, it's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution, or is there a grander design at work? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of a puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green suspended in the vastness of space, a planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field, all these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. And the Milky Way is just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet, despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason: it has life. It's the only known celestial body where life not only originated but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images and the reason life exists on Earth. But in the context of the cosmic web, the Sun is just one node, a lone star among countless others. Close to the Sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our Sun is located in the Orion arm of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars in the great expanse of the cosmic web. Stars like our Sun form complex nodes that connect larger structures such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So, what powers this celestial beacon? The answer is nuclear fusion. Deep in the Sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the Sun but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life, drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the Sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the Sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the Sun. Although the Sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. These are small, cool stars, also called M-type stars, often less than half the mass of our Sun. They make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal, turning hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the Sun and can be 1,000,000 times brighter. Yet they live fast and die young, often in spectacular supernova explosions. O-type stars dramatically end their lives, collapsing under their own gravity and then exploding as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. Different types of stars are born in these clusters, which serve as nodes in the cosmic web, linking different regions of the galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out that stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, making them denser and hotter until nuclear fusion ignites, and a new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our Sun is now. But even stars like our Sun must face change. In about 5 billion years, the Sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the star's final fate. Depending on its mass, a star will meet one of several ends. Stars with less mass, such as our Sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death throes of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light-years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static, they are in constant motion. Some may be heading toward the center of the cluster, while others may be on their way to its edge under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters and, by extension, the cosmic web. But clusters are not the end of the story. They often group together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy, that stitch together the fabric of the universe? These hypothetical one-dimensional defects in spacetime could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they exist, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized but also why it is organized this way. However, let's return to structures of unfathomable scale, superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supercluster. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest structures for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies, and yet what we can see represents less than 5% of the entire universe. Standing on the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web, yet it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light-years away, we become not just spectators but active participants in this cosmic journey. Each new discovery is a step toward answering the eternal question that prompts us all to ponder: what other mysteries does the universe hold that we have yet to unravel? Imagine a universe just beginning, only a few 100 million years old, a time when the first galaxies were forming. Thanks to the James Webb Space Telescope, JWST, we've made groundbreaking discoveries that take us back to this ancient era. Before you is a universe where every tiny point of light is a galaxy, a vast cluster of stars, planets, and mysteries. Among these countless galaxies, some are so distant that their light took billions of years to reach us. Studying these distant galaxies is of great importance because it helps us understand the early stages of cosmic evolution and the formation of structures in the universe. This spring, astronomers using JWST were able to peer into the earliest universe, discovering galaxies that existed more than 13 billion years ago. One of these discoveries concerns galaxies with redshifts between 9 and 11. But what does that mean? Simply put, redshift is a measure of how much light from these galaxies has been stretched by the expansion of the universe. The greater the redshift, the farther back in time we're looking. The light from these newly discovered galaxies began its journey when the universe was less than 1 billion years old. At that time, our Milky Way was just beginning to form, and only the first stars were illuminating the cosmos. Not only are these galaxies incredibly distant, but they're also incredibly young, giving us a glimpse into the formative ages of the universe. So, how did galaxies like ours originate and evolve over billions of years? Let's find out. In the depths of space, hidden among countless stars, lies source 43833. This galaxy, located at a redshift of 8.76, takes us back to a time when the universe was less than 600 million years old. Its light, traveling through the vastness of space, brings us valuable information about the early stages of galaxy formation. Looking deeper, astronomers have approached source 16943, an even more distant galaxy with a redshift of 11.4. This galaxy is one of the oldest ever observed, emitting its light at a time when the universe was only 400 million years old. Studying such distant galaxies helps us understand the processes that led to the formation of the first stars. Finally, Mach 0647 JD appears before us, observed at a redshift of 10.17. This galaxy's light has taken more than 13 billion years to reach us. Its discovery was made possible by the powerful capabilities of JWST, revealing its complex structure and providing insight into the early universe. But what is redshift, and why is it so important? Imagine a car traveling away from you. Just as the car's taillights appear increasingly red as they move away from us, the light from distant galaxies is stretched and shifted toward the red spectrum. The higher the redshift, the more distant and ancient the galaxy is. Redshift is an essential tool for astronomers. It allows us to measure the distance to these galaxies and, therefore, their age. The light from these galaxies began its journey billions of years ago, creating a snapshot of the early stages of the universe. By studying galaxies at different redshifts, we can piece together the story of cosmic evolution. These galaxies are not just distant objects, they are time capsules that provide a glimpse into the early universe. These discoveries address fundamental questions about our existence. How did the first galaxies form? What processes drove their evolution? And what does this tell us about our home, the Milky Way? The discovery of these distant galaxies was made possible by two significant observing programs. These programs used the advanced capabilities of the James Webb Space Telescope, JWST, to look deeper into the universe than ever before. The first program used the director's discretionary time to focus on observing high redshift galaxies. Under the leadership of principal investigator Pablo Arabel, this program aimed to study the early universe, searching for galaxies formed just a few 100 million years after the Big Bang. By targeting specific regions of the sky, DD 2750 successfully identified several ancient galaxies, including Source 43833. The second program was part of an overall observational program led by principal investigator Dan Company. This program was aimed at detailed spectroscopic studies of known candidates for high redshift galaxies. The GO 1433 program was instrumental in confirming the redshifts of these galaxies and studying their properties in detail. As part of this program, the team observed two other objects, obtaining valuable data on their composition and structure. JWST used two of its most powerful instruments, NIRSpec and NRCam, to make these groundbreaking observations. Let's take a closer look at how these instruments work. NIRSpec, or near-infrared spectrograph, is designed to simultaneously obtain spectra of multiple galaxies. This instrument can analyze light from galaxies to determine their chemical composition, temperature, density, and redshift. It is crucial for studying the detailed properties of galaxies and understanding their evolution over time. NIRSpec operates in the near-infrared, which is ideal for observing distant galaxies. By dividing the incoming light into its constituent wavelengths, the instrument creates a detailed fingerprint of each galaxy, revealing its unique characteristics. NIRCam, or near-infrared camera, serves a different but complementary purpose. It takes high-resolution images of galaxies, allowing astronomers to study their morphology and structure. The camera is particularly effective at observing faint and distant objects, making it indispensable for identifying and analyzing high-redshift galaxies. NIRCam's wide field of view allows large areas of the sky to be captured in a single image. This capability is critical for surveys such as DD 2750 and GO 1433, where astronomers need to observe many galaxies simultaneously. By combining detailed spectra with high-resolution images, scientists can build a complete picture of these ancient galaxies. So, what exactly did the scientists see? These ancient galaxies are incredibly small compared to our Milky Way. They are less than a kiloparsec across, about 1,000 times smaller than our Milky Way. Despite their diminutive size, they're bustling with activity typical of the young, star-forming galaxies of the early universe. Some of them even exhibit complex structures affected by gravitational lensing, a phenomenon where a massive foreground object distorts the light from a background object, allowing us to see them in greater detail than would otherwise be possible. But why do these size differences matter? The small size of these galaxies suggests they're in the early stages of their evolution. In the young universe, galaxies were still forming and merging, leading to intense periods of star formation. These compact galaxies are like snapshots of the early universe, showing us how galaxies start their lives and grow over time. What do these galaxies look like? Source 43833, for example, appears as a bright, compact object with hints of structure indicating regions of intense star formation. Source 16943, although smaller, also shows signs of active star formation. In contrast, MAC 0647 JD shows a more complex morphology due to lensing effects, with multiple images of the same galaxy. However, understanding the light from these galaxies is key to unlocking their secrets. This is where spectral energy distribution, SED, comes into play. The SED represents the range of energy emitted by a galaxy across different wavelengths, from ultraviolet to infrared. By studying the SED, astronomers can infer various physical properties of a galaxy, such as its age, mass, and star formation rate. We use the NRSpec and NRChem data from JWST to create the SED, after which we can model it using software that simulates different galaxy formation and evolution scenarios. By fitting the observed data to these models, we can estimate the galaxy's stellar mass, star formation history, and other important parameters. The SEDs of these galaxies indicate a relatively young stellar population, with intense star formation occurring less than 100 million years ago. A detailed analysis of these SEDs helps us piece together the life history of these ancient galaxies. As we've already mentioned, the light from these distant galaxies contains a wealth of information, especially in the form of emission lines. Emission lines are bright lines appearing at specific wavelengths in the spectrum, occurring when elements in the galactic gas become energized and emit light. Each element produces a unique set of lines, much like a fingerprint, which allows us to determine the chemical composition of the galaxy. In addition to identifying elements, emission lines also reveal the physical properties of the galaxy's gas and stars. By analyzing the intensity and ratio of these lines, astronomers can estimate the rate of star formation, showing how many new stars are being born in the galaxy. For example, a strong H-alpha emission line indicates a high star formation rate, suggesting that the galaxy is actively producing new stars. The emission lines also help determine the oxygen content of the galaxy, which is an indirect indicator of its overall metallicity. This information tells us how many generations of stars have existed, enriching the galaxy with heavier elements over time. Understanding these properties helps compile the history of the galaxy and determine the stage of its evolution. One of the most intriguing features observed in these distant galaxies is the damped Lyman alpha system, or DLA. But what exactly is a DLA? Simply put, a DLA is a broad absorption line in the spectrum of a galaxy caused by the presence of large amounts of neutral hydrogen gas. This absorption line is much broader than normal lines, indicating a significant amount of gas. DLAs are important because they allow us to directly measure the amount of neutral hydrogen in the early universe. This information helps us understand how galaxies acquire the gas that fuels star formation and how they evolve. By studying the DLA, we can learn about the conditions in the universe when these galaxies formed. The detection of DLAs in these galaxies involves analyzing their spectra for characteristic broad absorption features. This process allows us to quantify the amount of gas present and understand the environment around young galaxies. The presence of DLAs in these galaxies tells us that they are rich in neutral hydrogen, which is crucial for star formation. It also provides insight into the intergalactic medium, the space between galaxies, and its role in galaxy formation. By comparing DLA features in different galaxies, we can build a more complete picture of the early universe. The discovery of these ancient galaxies provides a unique opportunity to compare them to other known superluminous galaxies. Unlike their more evolved counterparts, these newly discovered galaxies have distinctive characteristics that set them apart from others. What makes these new discoveries special is the unusual amount of dense gas surrounding them. This gas, consisting mainly of hydrogen and helium, is one of the earliest elements to exist in the universe. The presence of such dense gas is unusual because it indicates that these galaxies are in the earliest stages of their evolution. This dense gas is likely to fuel the formation of new stars, playing a crucial role in their evolution. Another unique feature of these galaxies is their low metallicity. In astronomy, metallicity refers to the content of elements heavier than hydrogen and helium in a galaxy. Low metallicity also confirms that these galaxies have not gone through many star formation cycles, which means that they have fewer heavy elements and that they are in the earliest stages of their evolution. Thus, they are an ideal laboratory to study the initial stages of galaxy formation and their evolution. This information will help us piece together the sequence of events that led to the formation of galaxies in the early universe. These discoveries also fit into the broader context of understanding the history of the universe. During the period known as the Age of Reionization, the universe transitioned from opaque to transparent. The galaxies discovered by JWST are among the first to contribute to the reionization process by ionizing the gas around them. The next steps will involve creating large statistical samples of galaxies to estimate in detail the prevalence and brightness of their features. Researchers will continue to study where the gas is, how much of it is near the center of galaxies, and whether it is primordial or already contains heavier elements. In the meantime, we await new results and discoveries, which we will be sure to report to you. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the ninth planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh Regio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a ninth planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shaped the orbits of the then-known celestial bodies around us. At the center of the search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky inch by inch in search of an elusive planet that had eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, the Hubble Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and an unyielding spirit of exploration. 5, 4, 3, 2, 1, we have ignition and lift off. NASA's New Horizons spacecraft set off on a decade-long voyage to visit Pluto and then beyond. In January 2006, humanity embarked on one of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission, to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Planitia, a nitrogen ice plain, stretched across the entire dwarf planet, its surface marked with a complex pattern of ridges and depressions. Among the most striking discoveries were signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanism indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes, it was a dynamic world full of surprises and beauty, waiting at the edge of our solar system. This was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark, it's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Planitia is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, which changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is marked by a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, turning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water, isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of Pluto's atmosphere defied initial expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant sun, though faint, is enough to cause a remarkable transformation. Surfaces composed of nitrogen, methane, and carbon monoxide begin to sublimate, a process by which these ices change from a solid state to a gaseous state without passing through an intermediate liquid state. This sublimation is most pronounced in regions exposed to the sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven and is influenced by Pluto's topography and the composition of its ices, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward the more distant parts of its orbit, the atmosphere undergoes a dramatic transformation. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. The dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from being a static frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate, which, unlike the strong magnetic fields and gravitational pull that protect the atmospheres of larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible, comet-like trail that Pluto leaves behind as it orbits the Sun. This leakage is not a steady, gentle flow but a complex interaction with the solar wind, a stream of charged particles emanating from the Sun. These particles collide with the escaping atmospheric gases, creating a dynamic and ever-changing environment around Pluto, a miniature magnetosphere where the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that challenge the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It's a whole world filled with geological wonders and a unique history that's intertwined with Pluto's. As New Horizons flew past Charon, it captured images of canyons so deep and wide that they could easily swallow parts of Earth's Grand Canyon. These chasms stretch across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet, in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side and vice versa, a phenomenon known as tidal locking. Unlike most moons that orbit around their planets, Pluto and Charon orbit around a point in space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system provide valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighborhood. Pluto, once thought to be the ninth planet, has found its relatives among the vast number of Kuiper belt objects, KBOs, from dwarf planets like Haumea and Makemake to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflects the complexity and diversity of the Kuiper belt. The Kuiper belt is a window to the past, a frozen archive of the birth of the solar system. The objects within it, including Pluto, are remnants from the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rock, provides insight into the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to reconsider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. Surely, you've heard by now that black holes can be so massive that they can outshine entire galaxies, but some of them are quite mobile, so much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints, frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars, and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze, intermediate-mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the globular cluster closest to Earth. What it discovered was nothing short of groundbreaking, a black hole with a mass about 800 times that of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But intermediate-mass black holes turned out to be a missing link, mysterious relatives everyone has heard about but no one has met. An equally interesting question is how these intermediate-mass black holes form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass, like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,857 miles away, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system where one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the reclassification of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. Gaia's main task is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered as the closest known black hole to Earth. Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments can measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to explore astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue, and how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole located 5,000 light-years away from Earth. This black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 meters per second. The key to this revolutionary discovery lies in a phenomenon predicted by Einstein's general theory of relativity known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star, creating a brief brightening phenomenon, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. This is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling, about 28 meters per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star, sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions such as the European Space Agency's Gaia Telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradles of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas towards the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower. If it's too small, it catches up due to the abundance of gas and dust in the galaxy. Yet, some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops, and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young gas-rich galaxies serve as the birthplace of various black hole phenomena, whether they're luminous black holes or intermediate mass wandering black holes hurtling through space, or the nearest black holes to Earth. Their origins can often be traced back to these bright young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of spacetime. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, LIGO, in 2015, opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that paint a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond, the throw of a stone creates an isolated ripple. In a stormy sea, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merged to form larger galaxies like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discovered that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And, of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal? In the 21st century, humanity finds itself at a crossroads, at a moment in history when we can see the stars but not yet touch them. Born in the era between exploring our own planet and the possibility of reaching other worlds, we stand on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and our place in the universe. Imagine a future in which Earth faces an existential threat, a catastrophe like a collision with an asteroid, climate collapse, or something completely unforeseen. Our solution: build generation ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generation ships, traveling at a significant fraction of light speed, could traverse vast distances between stars. With technology such as matter-antimatter engines, compact fusion drives, and even black hole propulsion, what seems like science fiction could become a reality. But these ships are not just vessels, they are lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenges of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth, with its social structures, cultural heritage, and daily challenges. What would it take to build such a ship? How can its inhabitants survive and thrive? Join us as we delve into the intricacies of interstellar travel without exceeding the speed of light. Today, we'll try to unlock the secrets of how humanity can one day travel to the stars, not in an instant, but through generations. Planning for interstellar travel is not only about technology but also about predicting why such travel might become necessary. Foreseeable threats to humanity's survival may force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself: comet impacts. Throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate shifts. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already led to significant changes in our climate: rising temperatures, melting polar ice caps, and increasingly severe weather events. If these trends are not controlled, Earth could become hostile to human life, making the search for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carry significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios where humanity faces a threat from its own creations. Uncontrolled AI or engineered pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as our species searches for a new home. Proxima Centauri b is a prime candidate, located just 4.24 light-years away in the Alpha Centauri system. It is the closest known exoplanet in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient of life. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that is smaller and cooler than our Sun, meaning the planet would have to be much closer to its star to be in the habitable zone. This proximity, while favorable for retaining heat, also exposes the planet to flares and radiation, which must be considered when planning human habitation. Current research indicates that the planet has a mass similar to Earth's and may have a rocky surface. However, much about it remains unknown, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be needed to collect more data and assess its suitability for life. Sending a spacecraft to our nearest neighboring star involves not only covering the distance but also ensuring that the destination is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri b was chosen as our target because of its relative proximity and potential habitability. However, reaching and inhabiting this distant world will be a monumental task, requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, where one crew sets off and reaches their destination within their lifetime, seem increasingly impractical when it comes to the vast distances between stars. This is where the concept of intergenerational ships comes into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sustaining ecosystems, with not only one crew on board but all of their descendants. Life on a generational ship is designed to mimic a small, self-contained world, with living quarters, food production, water recycling, and social systems. The concept is simple yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that for many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure that the inhabitants survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population, to cultural and educational programs that preserve and pass on vital knowledge and skills. Einstein's special theory of relativity presents a serious problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases, and they require exponentially more energy to continue accelerating. This effectively makes traveling faster than the speed of light impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory by accepting the duration of space travel and planning for generations of life aboard such ships. Humanity can aspire to reach distant stars. Such an approach recognizes the limitations imposed by the theory of relativity while at the same time supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, not the least of which is the vast distance between celestial bodies. To make interstellar travel feasible within a human lifetime, we have to take a closer look at advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time on board slows down compared to the time experienced by an observer at rest. This means that for a spacecraft traveling at a significant fraction of the speed of light, the travel time for the crew will be shorter compared to those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, time dilation would cause 1 year aboard the ship to be equivalent to more than 2 years on Earth. Because of this effect, Interstellar journeys stretching over decades or centuries may seem shorter to the crew, although they do not shorten the actual distance. Several advanced propulsion methods have been proposed to achieve the high speeds required for interstellar travel, each with its own set of problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets, potentially allowing spacecraft to reach significant fractions of the speed of light. However, producing and storing sufficient antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the Sun, to produce energy by combining light atomic nuclei, such as hydrogen, with heavier nuclei. These reactors could provide sustained and powerful thrust for spacecraft. However, while controlled fusion technology holds promise, it is still under development, and building a compact and reliable reactor suitable for spaceflight presents another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the enormous gravitational energy of a black hole to propel a spacecraft. The idea is to create a small artificial black hole and harness the energy of the Hawking radiation it emits. Theoretically, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes is still in the realm of science fiction, far beyond our current capabilities. However, the challenges don't end with propulsion. Traveling at near-light speeds is fraught with many dangers. One of the main ones is the threat posed by interstellar particles. At these high speeds, even tiny particles can cause significant damage in a collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious hazard. High-speed space travel exposes the crew to intense cosmic radiation that can have harmful health effects. Effective radiation protection, and possibly even medical interventions, will be necessary to keep the crew healthy during long-duration missions. Maintaining the structural integrity of the spacecraft over the long term is also critical. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the voyage. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. By researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we are taking crucial steps toward reaching for the stars and expanding our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it's important to explore both best practices and traditional methods. One promising approach is to scale up traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravitational assists to achieve unprecedented speeds. The probe is traveling at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light, making it the fastest man-made object to date. Its propulsion system is based on hydrazine thrusters powered by solar energy, demonstrating the potential of using existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase the speed of a spacecraft without expending additional fuel. By carefully planning a trajectory, a spacecraft can gain significant speed, reducing travel time over vast distances. This technique, while insufficient by itself for interstellar travel, can be an important component of a multi-stage propulsion strategy. Scaling up these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are highly efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. For faster travel, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is the Orion project. First proposed in the 1950s, this method involves a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the spacecraft forward. The Orion project uses a massive pusher plate at the rear of the spacecraft, designed to absorb shock waves from explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft could reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still have to be solved. Controlling the timing and direction of the explosions requires precise design, and the spacecraft must be designed to withstand enormous loads. Additionally, the environmental impact of launching such a vehicle from Earth must be carefully considered, which may also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would make it possible to travel to the nearest stars within a human lifetime. Fusion propulsion offers a more controllable and potentially safer alternative to the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still under development. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, safety, and performance. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts, such as the Orion and Daedalus projects, promise the potential for faster and more ambitious interstellar travel. Ensuring the survival and health of the crew over multiple generations is a cornerstone of generational ship planning. One of the most important aspects is maintaining genetic diversity, which is necessary to prevent inbreeding and genetic diseases that could jeopardize the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over many generations by introducing various parameters, such as initial population size, mutation rates, and reproductive patterns. These simulations can provide insight into the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. They also take into account possible random events, such as accidents or disease, that could affect the population. Such modeling is essential to creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be educated about the importance of genetic health and the steps necessary to maintain it. This includes monitoring genetic diversity and making informed decisions about partnership and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies by scientists such as Frederick Moran and Camille Bawley, who have extensively studied the genetic dynamics of small isolated populations. In their research, Moran and Bawley use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that with a balanced sex ratio and optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding will not jeopardize the health and viability of future generations. An initial population of 100 individuals should grow to 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The modeling takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes, to ensure the sustainability of the population. Designing a generational ship to accommodate a growing population involves planning for adequate living space, resources, and social structures. The ship should provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. This includes collaborative activity spaces and private living quarters to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it is vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for mission success. Effective crew and population planning is essential to the success of a generational ship. Using advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. Above all, designing a generation ship capable of sustaining human life for centuries involves creating a self-sustaining environment that mimics the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources such as water and air. These systems must be reliable, efficient, and able to operate autonomously for long periods. One of the most important aspects of ship design is the creation of artificial gravity to maintain the health and wellness of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To counteract these effects, generation ships can use rotating modules to create a centrifugal force that mimics Earth's gravity. The most practical design involves a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes the occupants outward, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a rate of about 3 revolutions per minute to create an artificial gravity of 1 g, similar to Earth's. This design not only helps maintain physical health but also provides a familiar environment that can alleviate the psychological challenges of living in space. Rotating habitats can include living quarters, recreational areas, and workspaces designed to optimize the use of available space and resources. Reliable and efficient food production systems are also required to sustain populations for generations to come. Hydroponic and aeroponic systems offer solutions for growing crops without soil, using nutrient-rich water or mist to nourish the plants. These methods are highly efficient, use less water in space than traditional farming, and are well suited to the controlled environment of the ship. Hydroponic systems involve growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to the roots. Both systems can grow a wide range of crops, from leafy greens to root vegetables, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and breeding could increase the yield and nutritional value of crops. Efficient water and air recycling are critical to the sustainability of a generation ship. Water recycling systems must be capable of recovering and treating wastewater, ensuring a continuous supply of clean water for drinking, cooking, and irrigation. Advanced filtration and purification technologies, such as those used on the International Space Station, ISS, are already achieving high levels of efficiency. On the ISS, for example, the water reclamation system can recycle up to 98% of wastewater, including urine and sweat. This level of efficiency is necessary for long-duration missions when resupply from Earth is not feasible. Future generation ships will need to improve this efficiency even further, aiming for near-complete recycling to minimize the need for large water reserves. Air recycling is equally important, requiring systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen but also contribute to the psychological well-being of the crew by providing a connection to nature. Projects such as Biosphere 2 have demonstrated the potential for creating closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of such systems, providing valuable lessons for the design of life support systems on generational ships. Creating a self-sustaining generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the pillars of this design, enabling humanity to embark on a long-term journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship. It requires meeting the mental, social, and educational needs of the crew, ensuring their health, motivation, and cohesion throughout the long voyage. Isolation and confined spaces can significantly affect morale and mental health. The lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, depression, and anxiety. Addressing these issues is critical to maintaining a stable and motivated crew. Virtual reality, VR, technologies offer promising solutions for mental health and cultural connection by creating immersive simulations of terrestrial environments. Virtual reality can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, helping to alleviate feelings of isolation and maintain a connection to their home planet. Artificial intelligence, AI, can also play an important role in supporting crew mental health. AI therapists, such as NASA's Simon 2.0, can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflict. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to mission sustainability. A comprehensive education system must be put in place to ensure that each new generation receives the necessary skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar voyage requires not only technological prowess but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technology, such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will create the foundation for a thriving community across generations. When we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Wennu, is not a single form but a cluster of a dozen rocks, each more than 3 meters wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between the two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is filled with potential concepts for the next New Horizons missions, already stirring the imagination of scientists and engineers. One of these envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes using Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn mission, and could potentially go beyond the Pluto system to explore new frontiers in the Kuiper belt. New technologies, such as direct fusion drives, promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled The Fusion-Enabled Pluto Orbiter and Lander, from NASA's Innovative Advanced Concepts (NIAC) program, describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten travel time, opening new pages in the exploration of the distant worlds of our solar system's outskirts. As we traverse the vastness of space, exploring distant worlds and uncovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the ninth planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporary shift, Pluto's overall trajectory ensures there's no risk of collision with Neptune due to their mutual orbital resonance. The lengthy debate over Pluto's planetary status has long sparked discussion and controversy, reaching far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of a planet in our solar system, leading to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper belt serve as beacons, guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe.